Alright, so let's now develop our theory of magnetostatics. And we're going to do that by considering the following simple experiment. Imagine we have two current carrying wires. Wire 1 carries current I1, wire 2 carries current I2, and there is a distance r between the wires. Now, if we were to set up this configuration, what we would find is that for currents flowing in the same direction as I've drawn them here, we would get an attractive force between the wires. That force would drop off as 1 on the distance squared. If we reversed one of the currents, we would get a repulsive force between the wires, but the force would drop off again as 1 on the distance squared, 1 on the distance between the two wires squared. You'll notice that we have some similarities and differences to electrostatics. Similar to electrostatics, the force decreases as 1 on r squared. Different to electrostatics, our sources are clearly vector sources. In electrostatics, our sources were scalars, they were charges. In magnetostatics, they are vectors. The direction of the current matters in the force law. So any force law that we would develop is going to have to take account of the vector nature of those sources. So let's quantify this, write down a force law and study that force law. Okay, so here is our force law. I've written this as F12, and I mean here the force on element 1 due to the presence of the current flowing in element 2. Alright, so in this particular configuration where the currents are parallel, so I should be clear about that, where the currents are parallel, the force is attractive. So we should find, if we were to analyze this, that the force on element 1 is in this direction. Okay, so if you were to analyze the cross products in the equation here, you would indeed find that for dl1 parallel to dl2 and this choice of the direction of the unit vector, that the force on element dl1 is towards element dl2. You'll notice that we have taken account of the vector nature of the force law through these cross products, and if I were to reverse the direction of either dl1 or dl2, I would reverse the sign of the force. You'll notice that the force drops off as 1 on the square of the distance between the two elements, and we have some constants in here which really are just a consequence of our choice of using SI units. Now, at this stage in electrostatics, you'll remember that we chose to write the force law in terms of an electric field. We really invented the electric field to rewrite the force law, and in the same way we're going to invent the magnetic field. And we're going to identify part of this equation in the force law as a magnetic field. And the choice we're going to make is the following. Let's identify this piece here, and we'll group in the choice, we'll group in these constants. These terms we're going to call the magnetic field at location R1 due to the current flowing in differential element dl2. Right, so we'll write that in the following way. Alright, so there we have grouped all of these pieces together. So here the magnetic field due to element 2 at location R1 is proportional to I2 and drops off as the square of the distance between them. Okay. Again, in analogy with electrostatics, we're now going to write the force law, this force law, in terms of the magnetic field, just as we wrote the electrostatic force law in terms of the electric field. Okay, so we've now we've now completed, if you like, our development of the idea of a magnetic field. We have a formula for it, we know how it enters the force law, but what we'd like to do now is we'd like to study the properties of the magnetic field. Remember, in electrostatics we developed the idea of an electric field, and then we looked at the divergence of the electric field and the curl of the electric field, and we developed two of our Maxwell equations, at least that are applicable at least for electrostatics. We'd like to do the same thing here, but again we're going to introduce our change in notation, where we're going to denote a source position by a primed coordinate and a point of observation by an unprimed coordinate. And this is really a very simple but very powerful notation. So let's do that first, and then we'll look at divergence and curl. Okay, so we've set up our standard coordinate system here. We have an element of current IDL prime located at position R prime, and we're interested in the magnetic field B at position R. And of course, both R prime and R here are quite general. They're quite arbitrary. We can move R prime around, we can move R around, and our formula must reflect that. Here I've written the magnetic field at R. We've got our constants, which are a choice of SI units, and you'll see that we have this is really the same equations on the previous page, apart from the fact that we've changed to this rather more general notation, where we've denoted source terms with a primed coordinate and observation with an unprimed coordinate. Okay, now strictly speaking, probably I should really write this as dB of R, meaning that we have a differential contribution to the magnetic field, a dB here, due to the presence of IDL. In reality, of course, this could not exist in isolation. The wire would have to be a current loop, and so what we would really have is we'd have some loop of wire that might look like this, and to calculate the total magnetic field at B, we would integrate around the loop. So to do that, we would then simply do the following. Let's just integrate with the understanding that is around the loop, and then we'll remove the dB on the left hand side, and we have the full magnetic field. Okay, so this then is our expression for magnetic field, at least for a one-dimensional line current. At this stage, at the analogous stage in electrostatics, we made another change. Instead of dealing just with charges, we moved to the idea of a charge density, and we integrated out over a volume. This is so we could take account of a distributed source of charges. Now, similarly, no current distribution is really one-dimensional. It has size, it has volume, and we're going to have to develop some idea of a current density. So let's develop that now. So imagine I've got it's like a fat wire, if you like, or a volume in space. It doesn't have to be a wire. But the important bit is that I'm going to have a current flow in here, and that current flow can be a function of position. And we're going to introduce a vector quantity. I'm going to call it J of R prime, which has units of amps per square meter. And the idea is that if I want to know the current flowing across a given area, so let's say I had an area over here, there we go, and that area, let's call that area dA, that the current flowing across the area dI would be J at R prime dot dA, and clearly this has units of amps, has units of current. Now you'll notice if I were to introduce this expression for dI, or this expression for I, up into the equation we've put here, we will get terms that look like dA times dL, and that of course has units of volume. Now I'm not going to do the complete derivation here. You can look it up in Griffiths or Jackson or any of the other classic books, but the important bit is that those dA's and dL primes become a volume element. and they allow us to write the magnetic field in the following way. Okay, so let's study this equation. We now have an equation which takes account of extended extended current distributions through our idea of a current density. It's a vector, and the integral now runs over the entire volume, which includes all our sources. Now this d3r prime that I've written over here, this is just my notation for a volume element. In Cartesians it would be dx prime, dy prime, dz prime, for example. Okay, so there it is. There is our most general expression for the magnetic field. What we would like to do now, and the topic of the next segment, will be to study we're going to take a look at the divergence of the magnetic field and ask what is that, and we're going to take a look at the curl of the magnetic field.